For decades, fusion power has lived in the same mental category as flying cars and time machines. Always almost ready, always 5 years away, always just beyond reach. Every generation hears the same promise: unlimited clean energy, no carbon emissions, no meltdown risk. And every generation watches the deadline slip. But something feels different now. Quietly in Malaga, Washington, a company called Helion Energy is pouring concrete, installing hardware, and betting its credibility on a single claim: fusion electricity on the grid by 2028. This is the story of Helion's Orion site, and whether fusion is finally about to leave the lab and enter real life. Helion is not new to bold promises. The company has been working on fusion for over a decade, backed by serious capital and serious names. What is new is that Helion is no longer talking in abstracts or lab experiments. In October 2025, Helion received a critical permit approval for its Orion fusion power plant site in Malaga, Washington. That approval quietly marked the transition from theory to construction. No press hype cycles, no flashy countdown clocks, just permits, earthworks, and timelines. In the world of energy infrastructure, that's where reality begins. The Orion site isn't a test lab. It's not a demonstration hall for investors. It's designed as Helion's first grid-connected fusion facility, intended to generate electricity that actually flows into a power system, not just lights up a sensor. That distinction matters more than most people realize. Fusion has produced energy bursts before. It has achieved net energy gain in controlled experiments. But producing electricity reliably, repeatedly, and cheaply enough for the grid is a completely different challenge. Orion is Helion's attempt to cross that line. To understand what's happening in Malaga, you need to understand Helion's approach to fusion, because it's very different from the massive tokamak reactors most people imagine. Helion doesn't use giant donut-shaped machines or steady-state plasma confinement. Instead, Helion uses pulsed magneto-inertial fusion. In simple terms, they smash together two plasma rings at incredible speed, compress them magnetically, and trigger fusion reactions in rapid pulses. Each pulse is short, intense, and designed to produce usable energy directly. Here's the key insight that separates Helion from most fusion projects. They aim to generate electricity directly from the fusion reaction, without boiling water, spinning turbines, or relying on traditional steam cycles. The fusion reaction induces electric currents in surrounding coils, allowing power to be captured electrically. Fewer steps, less complexity, smaller footprint. On paper, it's elegant. In practice, it's brutally difficult. That's why the Orion site matters so much. This is where Helion has to prove that its approach works not just once, but thousands of times per day, day after day, with reliability that utilities demand. Fusion doesn't get credit for being clever. It only gets credit for being dependable. After the October 2025 permit approval, activity at the Malaga site accelerated. Site preparation moved forward quickly. Grading, foundational work, utility connections, and early infrastructure installations began almost immediately. This wasn't ceremonial, it was purposeful. Helion's leadership knows that every month lost now pushes their 2028 target further out of reach. And unlike past fusion efforts, Helion has tied its credibility to a specific commercial deadline. Let's talk about that deadline, because this is where skepticism is justified. 2028 is not far away. In energy infrastructure terms, it's practically tomorrow. Traditional nuclear plants take decades. Even solar farms take years from permitting to grid connection. Fusion plants combine advanced physics, high-voltage systems, exotic materials, and precision manufacturing. Hitting a 2028 grid target requires everything to go right: permitting, construction, hardware validation, control systems, and regulatory acceptance. And yet Helion is pushing forward anyway. The Orion facility is designed around Helion's next-generation fusion machine, building on lessons from earlier prototypes like Trenta and Polaris. Those earlier systems demonstrated key physics milestones: plasma stability, magnetic compression, fuel handling. Orion is where those lessons are supposed to scale into a power-producing system. Not theoretical megawatts, actual electrical output. What's happening at the site right now reflects that ambition. Construction isn't focused on a single monolithic reactor hall. Instead, the layout emphasizes modularity, high-speed electrical systems, capacitor banks, power electronics, and robust safety infrastructure. Fusion may not carry meltdown risks, but it still involves extreme energies, powerful magnetic fields, and high-voltage equipment. The site is being built to industrial standards, not experimental ones. Here's an important point that often gets overlooked. Helion is building Orion as if it must work, not as if it might work. That mindset changes everything. When a project is framed as an experiment, tolerance for uncertainty is high. When it's framed as a grid asset, tolerance drops to zero. Utilities don't care about scientific elegance. They care about uptime, predictability, and maintenance schedules. This is where Helion's story diverges from Fusion's past. Fusion has historically been a government-funded science project, optimized for learning rather than delivery. Helion is treating Fusion like a product. That doesn't guarantee success, but it does force discipline. Deadlines matter. Costs matter. Failure has consequences. Now let's address the elephant in the room. Will Fusion actually hit the grid by 2028? The honest answer is it's possible, but not guaranteed. And anyone who tells you otherwise is selling confidence, not reality. Helion has made impressive technical progress, but Orion represents a leap in complexity. Scaling from prototype pulses to sustained power output is where fusion projects traditionally stumble. Thermal stresses, component wear, control system stability. These are problems that only show up when machines run continuously. But here's why Helion still deserves attention. They are attacking the problem in a way that reduces exposure to some of fusion's worst traps. By avoiding steady-state plasma confinement, they reduce material fatigue from constant heat loads. By capturing energy electrically, they avoid inefficient thermal conversion. By using pulses, they gain opportunities for control and diagnostics between cycles. None of this makes fusion easy, it just makes it less impossible. The Malaga site itself plays a strategic role beyond engineering. Washington State offers access to clean electricity, skilled labor, and grid infrastructure suitable for experimental interconnection. It also places Helion close to technology partners and supply chains critical for high-speed electronics and advanced manufacturing. Orion isn't isolated in the desert. It's embedded in an ecosystem that supports iteration. And iteration is everything. Fusion doesn't succeed by getting it perfect the first time. It succeeds by improving rapidly once real-world operation begins. Orion doesn't need to be the final answer. It needs to be the first working answer. What makes Orion especially interesting is that Helion isn't trying to power an entire city on day one. The initial grid connection is expected to be modest, proof of function rather than mass deployment. That's smart. It lowers the bar for initial success while still delivering the milestone that matters most: fusion electricity delivered outside the lab. Once that happens, the conversation changes. Investors stop asking, "Is fusion real?" and start asking, "How fast can it scale?" Governments stop funding research and start funding deployment. Utilities stop watching from a distance and start negotiating contracts. Orion doesn't need to solve everything. It just needs to work. Now ask yourself this: If fusion finally works, even at small scale, who benefits first? It's not households, it's data centers, industrial facilities, remote installations, places where power reliability is more valuable than low cost. Helion understands this. Orion is a stepping stone, not a consumer solution. That's why 2028 matters symbolically more than economically. Fusion on the grid by 2028 won't revolutionize energy overnight, but it will prove that fusion belongs in the real world. And once something belongs, it tends to grow. As of now, Helion's Orion site stands at a crossroads. The permits are approved, construction is underway. The physics has been demonstrated at smaller scales. The timeline is aggressive, the risk is real. So will fusion actually hit the grid by 2028? It might. And for the first time in fusion's long history, that answer doesn't feel like a punchline. Let me leave you with this thought, and I want you to really sit with it. Every major energy transition began not with perfection, but with a first imperfect machine that worked well enough. Steam engines exploded. Early power grids failed constantly. Solar was once absurdly expensive. What mattered was crossing the line from idea to operation. Helion's Orion site is attempting to cross that line. Whether it succeeds or not, the attempt itself signals something important. Fusion is no longer hiding behind distant promises. It's standing on a construction site, on a schedule, with a grid waiting. And soon we'll find out whether this time, the future actually shows up.